0 and minus V, isn't it? But still, when you see the pole voltage, that means midpoint of your source and the midpoint of your line, V0, V1, V1, you can see it is again V by 2 and minus V by 2, this one. So there is no 0, 0. So when we stage a three-phase inverter at 180 degree mode of operation, actually the voltages that are appearing the output is a 3 level, but we don't call 3 level, we call it 2 level, just because it's matter of the pole voltage. Other things I think we not explain, the voltage just remains same. So now I think these operations are very well known, 180 degree mode of operation and 120 degree mode of operation, whatsoever it is. Now, as I have told you, now when we want to go for our advanced applications, so the voltage sustainability by an inverter is having a specific range. Beyond that, we cannot be able to operate it. So what we need to do, we need to go for multi-pulse inverter. So what we do, we can connect two inverters, which can be connected to a transformer, and they are coupled. The secondary side of the transformer is coupled, so that the inverter 1 gives a voltage, inverter 2 gives a voltage, and both the voltages in series induced in the secondary windings in series, and actually we will be able to attain a high voltage. In this case, it is important to note that your voltage problem resolves. That means when you want to go for high voltage applications, you can go for a multi-pulse inverter topologies, wherein you are able to enhance your voltage capability of an inverter. But still we will call this as a two-level inverter, because the inverter one and inverter operate as two-level and their voltage range or extensive voltage range is not going to be enhanced. But additionally, when you want to go for this type of thing, you need to go for a transformer which is increasing the bulkiness of your inverter. And now coming to the point. So as I was telling you, if when you go for a transformer operation, as you are seeing on the screen, what should be the phase difference between the V0 and V02? That matters. Because when inverter 1, if you see the voltage of an inverter 1, your voltage is something like this VAB. If both the inverters are connected to multi-pulse inverter in the same phase, what happens? You will get the same type of voltage here, but the voltage level is more because the upper inverter gives some 100 volts, let us say, lower inverters give 100 volts. If the shape of the voltage is same, you will get 200 and 400 probably. But ultimately what happens? The output voltage shape remains to be same. Understand one point, like when we talk about power quality, because nowadays wherever you go for any sort of power electronic converters, power quality plays a vital role. That means, what is a power quality? If you have a question, in general, when we are operating or when you are using any type of application, and when you are supplying a voltage to an application, until unless your frequency is within the range, and if your input and output voltages are as prescribed by the nature of the application, like first of all, if you are using a rectifier, so your input is AC and your output is DC. In an ideal condition, what should be your input voltage? It should be sinusoidal voltage, isn't it? Sinusoidal voltage. When it is drawing a current from the source, what should be the nature to say that the quality of the power is good? It should be sinusoidal. And what is the next point? Power factor. Because once the power factor is unity, it is having the best power quality. So let us say if you take a rectifier input voltage will be sinusoidal because we give. So at the same time, the current that is drawn from the grid should also be sinusoidal and it should be in phase with the voltage. And let us now come to the other side, to the DC side. What is the DC side? We are rectifying the voltage. What about the rectified voltage? It is a DC. When we talk about it is DC voltage, what should be the ideal case? Straight line. With the current, again a straight line. The parameter would be different. But ultimately, the nature of the DC network, it should be a straight line. But when we use or when we try to convert the AC to DC or DC to AC by using polar converters, the voltages which is given by the user will be constant, but the behavior of the current is not as ideal as I am saying you, it should be sinusoidal. Because in case of inverter, if you say the nature of the voltage that we are giving to an inverter will be DC, which is straight line. But what is the output nature? It is not sinusoidal. It is also it is either square wave or it is a quasi square wave. So ultimately what happens when you are trying to operate such voltage connecting to application, due to the harmonic content in the output voltage, it will disturb your loads and it will change the characteristics of your load, because your load which is connected to the inverter is designed for its characteristics attained at the ideal case of voltage and current. But when such ideal case of voltage or current is not appearing to your application will go for malfunctioning. So when we are going for the polyphonic converters used for our purpose, because when we go for applications, advanced application, we have AC to DC conversion, we have DC to AC conversion, we have AC to AC where we need a frequency control, and also we need to have a DC to DC control where we need a various level of DC voltages in a complete application. We need DC converters. Everywhere we are going to use the inverters, converters or DC converters. But what is the main role of the controllers is these parameters, what I was now able to tell you, those parameters should be controlled by some or other control schemes which we need. And the controllers play a vital role in such aspects. But before knowing that, you should understand that what is the conventional problems that we observe, what are the practical problems which we observe, so accordingly we can easily mitigate the issues. So same thing, so here the voltage that is attained by your inverter is of a square wave, and when you are now connecting to a multiples inverter, and if you are interacting both the voltage in the same phase shift, there will be no change of the output phase voltage. The shape also remains same. So what happens? The inverter, the transformer's windings can be given a phase shift such that you get the best total harmonic distortion. So if you observe with a phase shift of 0, you get the same shape. It is the same shape of the voltage which you are getting in the case of the inverter. So if you go for 30 degrees, you get that shape 60, 90, 120 and 150. If you go for total harmonic distortion, if you calculate, you get the best at 30 degrees, because that is likely to be more sinusoidal and it is having better enhancement of the. So coming to the point, so the shift of the transformer this should be 30 degrees, and the 30 degree shift we call it as, how can we get it? One winding can be a star connected and the other can be a delta connected. So the shift of the two windings will be 30 degrees, and your output voltage will sum up and appear like as you are actually here, phi is equal to 30 degrees. And that phase shift is generally calculated by 360 degree divided by the pulse number. Because here the inverter is of 6 pulse inverter, inverter is of 6 pulse inverter, so you get the total of 12. So 360 by 12 will give the phase shift of the transformers. So that's why with the phase shift you will be able to attain the sinusoidal voltage. But what was recorded, you will get the sinusoidal voltage, but the voltage is enhanced. But what happens? The bulkiness of your inverter is increasing. Also, so other point, like if you go for sinusoidal variability, this is one more thing which we need to interconnect